Question 18. A solid sphere rolls down two different inclined planes of same height but different angles of inclination. If we hit the bottom with the same speed in each case, will it take longer to roll down one plane than the other? If so, which one and why? So this question we have already solved. Okay, question number 25 in previous chapter. So please refer that. Now next question 19. A hoop of radius 2 meter weighs 100 kilogram. It rolls along a horizontal floor so that its center of mass has a speed of 20 centimeter per second. How much work has to be done to stop it? Hoop means it is hollow cylinder. Okay, it's just rolling down. So it has translatory motion and rotational motion. Therefore, its total kinetic energy means kinetic energy of rotation plus kinetic energy of translation. Kinetic energy of rotation and kinetic energy of translation. So is equal to half I omega square plus half mv square. Now, for hoop means hollow cylinder, moment of inertia is mr square, and we have the formula omega is equal to v square by r. So substitute these two quantities in the total kinetic energy formula. You will get a total kinetic energy is equal to half into mr square into v square by r square plus half mv square. So r square cancel, you can simplify. So you will get the answer mv square. And mass and speed, centimeter per second, you need to convert into meter per second. Both are given there so that you can find the value of total kinetic energy. Then next, question 20. Oxygen molecule mass is given. Moment of inertia I is also given. Okay. The mean speed of such a molecule in a gas is 500 meter per second. The speed is also given. And its kinetic energy of rotation is 2/3 of kinetic energy of translation. Kinetic energy of rotation, half I omega square is 2/3 of kinetic energy of translation, half mv square. Now you substitute the given values and find the value of omega. That's it. Now, question 21. A solid cylinder rolls up an inclined plane of angle 30 degree. Angle is 30 degree theta. At the bottom of the inclined plane, the center of mass of the cylinder has a speed 5 meter per second. So here, when it starts rolling upward, speed is 5 meter per second. Then how far will the cylinder go up? That means yes, you have to find it. And how long will it take to return back? Okay. So here also we can apply conservation of energy. From conservation of energy, we can have half mv square plus half I omega square. That is the total kinetic energy is equal to mgh. When it rolls at the maximum height, when it stops motion, its total energy is converted to potential energy. Now, that is half mv square, half mv square plus half I omega square. It's solid cylinder and its moment of inertia is mr square by 2 into omega. Omega is again v square by r square is equal to mgh. Okay, again h we have to see from the diagram. Okay, so we have h by s is equal to sine theta, or h is equal to s sine theta. It is equal to s sine theta. Therefore, this is equal to mg into s sine theta. Mg into s sine theta. Okay. Simplify the equation. When you simplify, you will get 3 by 4 mv square is equal to mg into s sine theta. Now you know the mass velocity at the bottom. The mass will be cancelled there. Velocity at the bottom, you know, g 9.8, theta 30 degrees, so that value of s can be calculated. Then afterwards, how long will it take to return to the water? Okay, we can try to follow a simple method for solving part B. Take the formula V is equal to U plus 8. V is equal to U plus 80. Then the final velocity is 0. So that acceleration is equal to minus U divided by T. Minus U divided by T. Then we can use the formula V square is equal to U square plus 2AS. Square plus 2AS. Again, V is equal to 0. Therefore, we can rearrange minus U square. U square we can take to the left hand side, it will become minus U square is equal to value of A we can substitute there. So minus 2 U by T into S. Now one U will be cancelled, the negative sign also will be cancelled, so that T is equal to 2S by U. Yes, you have calculated already. U is initial velocity 5, so that T we can calculate, and T will give you the time taken by the cylinder to reach at the maximum height. And the question is, how long will it take to return back? So it's double. 2T will be the answer to the part B. Okay. Now next question 23. A man stands on a rotating platform with his arms stretched horizontally, holding 5 kilogram weight in his hand. Angular speed of the platform is 30 revolution per minute, means nu frequency. The man then brings his arms close to his body with a distance of each weight from the axis changing from 90 centimeter to 20 centimeter. So initially it was 90 centimeter apart, now only 20 centimeter apart. The moment of inertia of the man together with the platform may be taken to be constant and equal to 7.6 kilogram meter square. So what is the new angular speed of the man? Is kinetic energy conserved in this process? If not, from where does the kinetic the change come about? Okay, so these are the quantities to be calculated. Okay, now first of all, we can have the initial moment of inertia I1. I1 is equal to moment of inertia of the man. It is given 7.6 moment of inertia of the man plus moment of inertia of the objects in his hands. So we have moment of inertia is mass into square of the perpendicular distance 2m r1 square. R1 is 90 centimeter, you have to convert into meter. So you will get the value of I1. So find the value of I1, 7.6 plus 2m, m is 5 into R1 is 0.9. Then similarly I2. I2 also we can use the same formula, only the difference is that here instead of R1 we need to use R2, that is 20 centimeter convert into meter. So we get I1 and I2. Now there is no external force here, so we can apply law of conservation of angular momentum. I1 omega 1 is equal to I2 omega 2. Again, I1 omega 1 is equal to I2 omega 2. Again, omega 1 is equal to 2 pi mu 1 and omega 2 is equal to 2 pi mu 2. Now substitute the values in the equation. When you substitute the values in the equation, simplify it, then find omega 1 is already there, mu 1 is there, so can find the value of omega 2. Value of I1 and I2 are already there. Now, is kinetic energy conserved in this process? Kinetic energy is not conserved. Okay. If not, from where does the change come about? See here, the man is doing work to fold his hands. Okay, the work done by the man is converted into increase in kinetic energy. Then next, a bullet of mass 10 kilogram. Bullet of mass 10 kilogram, speed 500 meter per second. Sorry, 10 gram. A bullet of mass 10 gram, speed 500 meter per second. Okay, fine. Gets embedded exactly at the center of a door. The door is 1 meter wide, weighs 12 kilogram. And find the angular speed of the door, omega of the door. The moment of inertia of the door is given ml square by 3. Okay, so here also we'll apply this is a collision, okay, between door and bullet. So we can apply conservation of momentum. Okay, again we can have I1 omega 1 is equal to I2 omega 2. I1 omega 1 is equal to I2 omega 2. Now here actually this is L1 is equal to L2. Now for bullet, the angular momentum we can take as R cross P. R cross P is equal to I2 omega 2. That is R cross MP. M is the mass of the bullet. Okay. R cross MB is equal to I2 omega 2. Now, R, the bullet is embedded exactly at the middle. So, R we need to take 0.5. So then I2 is given ml square by 3. Here L we have to take 1 because the entire door rotates with respect to the hinges. Okay. So now we can have R cross MV in R is 0.5, M is 0.01 kilogram, V is 500 is equal to capital M L square, capital L is 1 meter by 3 into omega 2. So exact omega 2, all quantities are given in the question. So angular velocity of the door omega 2 can be calculated. Then next question 27. Prove the result that the velocity v of translation of a rolling body for a height h. You are asked to prove this result. Already we have seen the total kinetic energy is equal to kinetic energy of translation plus kinetic energy of rotation is equal to potential energy, applying law of conservation of energy. So kinetic energy of translation is half mv square plus kinetic energy of rotation is half I omega square is equal to potential energy mgh. Now rearrange the equation. Half mv square plus half I. Moment of inertia generally we can take as mk square, where k is the radius of gyration, into v square by r square is equal to mgh. Now m is cancelled. So that half v square we can take common. Half v square into 1 plus k square by r square is equal to gh. Now from this equation you can find the value of v square. Then you will get the given equation which you need to prove. Now question 25 we have solved already. 26 is not required. Then come to question 28. A disk rotating about its axis with the angular speed omega naught, which is shown in the diagram, is placed lightly without any force on a perfectly frictionless tip. The radius of the disk is r. Then what are the linear velocities of points A, B, and C? Okay, linear velocities. So now point A is having linear velocity r omega naught because v is equal to r omega. Then B is having linear velocity again r omega naught because it is a frictionless surface. There is no friction at all. As there is no friction, both A and B are having same velocity. And point C, it is r by 2 omega naught. Now, will the disk roll in the direction indicated? No. Friction is required to start rolling. Here there is no friction. Now question 29 is also a similar one. Explain why friction is necessary to make the disk roll in the direction indicated, because a torque is required to start rolling. Torque means two equal and opposite forces. So when you push the disc, the friction will give the second force in the given pair of forces. Therefore, a friction is required to provide the necessary torque to start rolling. Without torque, it is not possible to start rolling. That is the reason already in the theory we have discussed it. Then, give the direction of frictional force at P. Okay, so here you can see when the disc rolls like this, point B is pushed backward. The point B is given a tendency to move backward. So friction will be acting towards right as indicated there. Okay, then what is the force of friction after perfect rolling start? Perfect rolling means friction is equal to 0. So again I repeat, we have discussed already, to start rolling we need friction, then only we will get the tangential torque for starting the rolling motion. But once you get the rolling, the rolling is started, then afterwards friction is not required. If friction is there, then rolling will gradually stop. For ideal rolling, friction must be 0. Now, next question 30. You can leave question 30, not required. Then question 31 we have already discussed. Come to question 32. Read each statement below carefully and state with reason is true or false. The first one, during rolling, the force of friction acts in the same direction as the direction of motion of center of mass of the body. When the friction, so at the starting, the friction is acting like this. When the disc is rolling in this way, the friction is there when the motion started. After the motion started, suppose again friction is present, then definitely friction is what happens? The friction will oppose the motion. Now here the question is rolling motion, force of friction acts in the same direction as the direction of motion of center of mass of the body. So here from this diagram we can see if it is there, every time it pushes the surface backward, so friction is acting in the opposite direction. So the statement given there is a false statement. Friction is not always opposite to the direction of motion of center of mass. Here you can see in the beginning, center of mass, when it rolls towards here, friction is also in the same direction, not in the opposite direction in the beginning of the rolling motion. Second, part B, the instantaneous speed of the point of contact during rolling is 0. The statement is true. So here we can see this point will have a linear velocity towards here, but the total disk has a velocity in the opposite direction. And in the rolling motion we have seen, in the ideal rolling, the velocity of point B is 0, because r omega is acting towards here, and r omega is equal to VCM. That is what we have seen. VCM is acting towards right, and ideally the instantaneous velocity of point B will be 0. Then part C, the instantaneous acceleration of the point of contact during rolling motion is 0. Instantaneous velocity is 0. What about instantaneous acceleration? It is not 0. It is just like an object thrown upward. At the highest point, velocity is 0, but acceleration is not 0. The same is applicable here also. Momentarily, velocity is zero, but the acceleration is not zero, so the statement is false. Then part D, for perfect rolling motion, work done against the friction is zero. That is true. For perfect rolling, friction is zero. So work done against the friction is also zero. Then next part E, a wheel moving down a perfectly frictionless inclined plane will undergo slipping, not rolling motion. Suppose there is no friction at all on the surface. The wheel falling down, we have only slipping, there is no rolling. Statement is true because many times we have seen friction is necessary to start rolling. If there is no friction, it is not possible to start rolling, only slipping will be